But our topic today is our processors and SoC discontinuities turning verification on its head. I think we're going to probably focus on RISC-V. I think most of the panel wanted to focus on that. We also decided that three major themes we're going to talk about. One is on the CPU verification. Obviously, RISC-V allows people to add new instructions, and does that change the way we do CPU verification? And also, the SoC verification we all felt was changing as well. There's now multiple accelerators with different types of workload and use cases. And coherence is always there and potentially becomes more difficult. So what are the new challenges in SoC verification? And finally, maybe looking a little bit more to the future is chiplets. A number of us now working on chiplets, and is that going to be a new verification challenge for us? My job here really is to make sure that we get the right questions and keep people on the topic and off their products. So we'll try and make that happen. I've got a couple of my own questions, but I think this will be more exciting if we get questions from the audience. I do realise that we're between you and your travel home, so we'll try and make it as exciting as possible. Okay. So, I guess Duncan, is Duncan Phelps to be going on this all the time? Because yeah. So we've asked each panel member just to do a 2 minutes introduction. And so let's keep to the 2 minutes as well. You're up first, Duncan.
Okay, good evening. So I'm Duncan Graham, I work for Imperial Software. And what we're looking at now is that, SoC verification, it used to be, or currently, it's the SoC outside of the processor IP. So now we've got RISC-V. RISC-V gives us the flexibility and the freedom to create new design iterations. But this also means that instead of the processor IP being something that was brought in-house from a mainstream supplier such as ARM, MIPS, now that's part of the SoC and part of the verification of the SoC. So we need new ways of going forwards of encompassing that processor IP verification as part of the SoC verification. And this requires us to look at things like the complexities of the processor, so the out of order, multiple processor cores, pipelines, and all these asynchronous events that can now be required to verify. And so we need new methods and technologies, but we want to build upon UVM, System Verilog, and everything that's currently already used in that new environment. And what we see is two ways that we have the running a test against RTL, running a test against a reference model and comparing them, or more importantly, the step and compare methodologies, where we're running a single instruction or a single asynchronous event on the RTL, and then we're calling into some Imperial DV, for example, that uses standards in order to provide the reference to check against and to make sure it's going forward. So RISC-V has given a lot of freedom, but it's now blurring where the boundaries are in terms of the SoC verification and making it much more difficult for people to do that verification.
Okay.
Before you go further, my mic is going to switch off.
Low battery.
Yeah.
Thank you.
Classic battery. You should be connected.
What?
We said the mic is go out with the power.
Okay. I'm not sure we need it so much anyway, but...
Yeah, I mean, normally it's connected, so the power
You can use
Thank
this
you.
laptop.
low power designs
Black
are
laptop.
harder than before.
Should verify that. That's all good.
Okay, so...
You have a cable?
It's not my machine.
Go ahead, Mike.
Yeah, that's...
You need to switch on.
It's all going on, but we should push on. Okay, so let's move to Boda next. It's on now. Okay, Boda Hope, Assistant English Engineer from IBM. So over to you, Boda, for 2 minutes, please.
Thank you. So I'm verifying microprocessors since 30 years now. I think is red good. Normally red is not good. Anyway, yeah. So I'm Bodo. I'm verifying microprocessors now since 30 years. I mean, mainly responsible for the pre-silicon verification of our mainframe, our system. So we have a very complex system with a lot of processors, and verifying coherency. We got a strong coherency model. So the problems here we talk about are not new to us, but there's a couple of things that makes this different now with RISC-V. One of the things is we spend a whole lot of effort to make sure the system works. I can't imagine that everybody who works on an SoC doing an extension for RISC-V wants to make that same effort. And I think there's basically I see two main challenges or changes that are common with this. I mean, the one thing is how can somebody extend RISC-V processors on an SoC to create a USP without verifying the whole processor again, right? And making sure that it can still calculate 1 + 1, right? At least we need to figure out how do we get any hangs, work together with it, especially if we're getting to some higher performance implementations of RISC-V, getting to, maybe even superscalar versions of it. I think that really increases the complexity incredibly on the system. I think that's the one big challenge that increases a lot of effort. And the second one that comes with it is, I think these extensions are typically also on SoCs. With the RISC-V extensions, they make a new function, right? And the new function is something that is not really new, but it's something that makes it exceptionally well. And I think performance is going to be a big aspect right now. And I think we know how to verify the functionality pretty well in verification. I think we're really good at that. But I think if we look at something where we want to create, a SoC kind of model with like maybe even multiple processors, coherency fabric, accelerators, and stuff like that. That typically requires software in order to figure out, does that feature really work how it's supposed to work with respect to performance? Most of the people are just so deep into, does that mean I should stop?
That means you should stop now. You should stop. Okay. Means I should learn how to use my phone as well. Yeah, it means you should stop.
I'm good.
Okay. So our next speaker today, who helps set up this panel, so thank you very much, David, is Dave Kelf, who's the CEO of Blecker Verification Systems. And watch out for the beeps, Dave.
Yeah, right. No, it's a scary panel. Okay. So yes, I'm Dave. I'm with Blecker. We are in the business of test content synthesis. And mainly at the SoC level, and more we're finding a lot of work, of course, in the RISC-V space. So when we look at verification and how it's expanding and changing, we can kind of think of it happening along like three axes. One is kind of the platforms that you are employing, going from simulation to emulation hardware, and even formal, right, Ashish? The second axis, kind of one of complexity. And the things we're being asked to verify, going from functionality, as you just said, Bodo, to infrastructure and SoC like coherency, security, safety, now microprocessor, microarchitectures, all of which have their own sort of variants and issues. And then the third thing, which would be just the basic complexity of these designs, the kind of fabrics that we're looking at these days, the fact that having to verify processor microarchitectures, we can't just rely on ARM to do it, that kind of thing as well. And so if you look at where RISC-V is at and the complexity of RISC-V, it's kind of on the end of all those three axes. And if you think about the microprocessor space, in the past, we've always, here he comes. we've always been able to rely on ARM or Intel to pour verification money. The rumor was that, correct me if I'm wrong, Philippe, that ARM spent something like $100 million every year on verification. If we're doing RISC-V verification and there's dozens of companies doing that work, none of those companies can afford to spend $100 million, or maybe Codesit will one day, or as they grow up. Okay, maybe they can. Maybe I'm wrong. But it's a lot of money. where does that investment come from? And I think the only way to be able to bring that together is with automation, where the companies providing verification systems can learn from each other and build up that kind of same level of verification excellence so we can actually verify these processes.
Okay.
Yeah. I made it.
And our final speaker today, or final panelist, I should say, is Philippe Luc, who's Director of Verification at Coherent.
I am Philippe. Nice to meet you, everyone. I'm glad to be here and to present CodaSIP. CodaSIP is a company who is developing RISC-V processors. There are only few companies in the world developing processors. It's quite a complex task. And to make it simple, because we don't think it needs to be complex to develop a processor. So to make processor development much simpler, we developed an internal language to describe from a higher level perspective, and we make RISC-V processors, which are smaller and faster, and high quality. We also provide to the customers the possibility to customize them. In the ML, IA industry, and most of the timing-sensitive algorithm in software, you really need performance. And you can go to the next range of processor, which bring 20% performance every year, roughly. Or you can go 10x performance by just adding a couple of instructions in your RISC-V processor. And at CodaSIP, we propose that to the customer, and so that the customer handles completely the addition of a few instructions. So the challenge of verification for us is not only to deliver high-quality processor, but also help the customer so that when he has a new instruction, all is working together. That's a nice challenge.
Okay. So, well, within time, thank you very much. So, I am going to invite questions from the audience as soon as possible. So just indicate with your hand if you've got a question. I know there's already a few people indicated that. So I'm going to come to you first, but I'm going to ask my question first. And then we'll come to you. But Tam will be ready with the mic. We'll be ready with the mic. So, and I think this was touched on by Dave as well, is that the business model. We all know how expensive it is to verify not only the CPU, and Bodo touched on it, that if you add instructions and you've got to verify the performance, and and then I think Philippe indicated that they've automated and provided automation through their own language to try and bring the cost down. But overall, for each panelist, how do you suggest we can bring down this cost of verification to make the RISC-V business model work?
Okay, so one of the things that we're looking at is standardization to allow reuse. So the RVVI interface, the RISC-V verification interface, gives a standard set of signals that a designer needs to bring out in order to get the information from the host RTL into a form that can be compared directly with the golden reference model. So this means that once you've created your test environment, verification environment once, you can then reuse that on a number of different projects. So that's one of the areas I think that's really going to make a difference going forward, and more RISC-V designs are brought out.
Okay, Dave?
Yeah, so I agree. But I'm not going to agree too much. But so automation and standardization, right? So we need to automate the flows as much as we can. Something that I think ARM and Intel have been really good at internally inside their companies is creating their own automation for their specific problems and then reusing that over and over again. So we need to automate what we're doing as much as we possibly can, and then standardizing on specific interfaces, test content, structures in general, the way we use certain tools like formal, like simulation, as much as possible, we can sort of standardize on that so the same techniques can be spread across all the people building and verifying RISC-V processes. Then we can start to sort of bring together all that investment, into like one collective group. Something that a few of the companies here have been talking about is a consortium where we actually combine the effort for RISC-V under one group, trying to create some common methodologies that we can then spread across all the different folks building these processes. And so, this is an ongoing effort as well. And I think the more we can do that, the more we can kind of start to bring some investment together and spread across all these development efforts.
Okay.
So I think what's really needed is a test case generator that has architectural knowledge, and it also has testing knowledge that you can feed with templates and that you can extend it. Whether it's with supporting the new instruction set, or importing firmware code, C code, whatsoever, and that can be used in various different modes, because I think it's not good enough to do something on software simulation. We need something that does offline generation that we can run software simulation on, but we need really test case generator that can do on-target generation on accelerators, on emulators, as well as on post-silicon. I think that's going to be key. Things that we see on some of the processors that we see today, which have a lot of ARM instances on it and stuff like that, which also need to attack coherency. That's also something where I think there's really a generator with knowledge required. That's really what I think is needed.
Okay, and do you see PSS as that language or not?
Well, PSS doesn't have any knowledge. PSS doesn't know anything about. I mean, PSS can be the means to an end, but somewhere you need the architecture knowledge and you need the test case generator knowledge. PSS has no idea how address translation works, right, for example, or whatsoever, or what a coherency model is. It just doesn't know. I mean, it can be, it can be means to it, but I personally do agree that I do think that we need to have test templates, and the programs need to be intelligent enough to do test case generation on their own, on the target that they verify.
Okay.
That's not what PSS, in itself delivers. There needs to be additional smarts that come on top of it.
Okay, we'll come back to that, I'm sure.
Keep it simple. I've seen the processor complexity being increased a lot in the last 20 years. 20 years ago, we just verified a processor with 50 directed tests. And that was a very famous processor that works very well. And today we have plenty of technology, plenty of very expensive tools, just to verify that because a very thin wire is connected from the very beginning of the processor down to the end to gain 0.1% of performance. We used to have an expression in the team saying that when we try to repair a leak in the kitchen and we fix the tap, it starts to leak in the bathroom. Each time you change something somewhere, there is a bug appearing somewhere else, and we spend a lot of energy doing that. So keep it simple, please.
Keep it simple. Okay, Tad, you want to move to our first question? Dave.
Keep the design simple or keep the verification simple?
Both.
Okay.
Both. If the design is simple, it simplifies your life.
Okay, let's move to our first. Yeah, first question will be good. Okay.
Hello.
And get ready for your next one as well.
Hi. You've talked a lot about computing, but memory is, getting more and more functionality, like control bandwidth, association with caches or not, encryption, real-time encryption. So if you look at ARM RAMs, for example, for V9 and even for Power, where you have everyone tries to avoid the noisy neighbors on the virtualization platforms. So how does it translate into verification of those aspects, like bandwidth? Like if you have also encryption, can it be hacked? Do you run verification of hacking capabilities? What's the level of verification that can be done on memory today?
That's a subject for the whole panel, I think, right? But you're absolutely right to ask the question to me. So when we look at these SoCs, right, and let's go back to RISC-V, a lot of the RISC-V SoCs today are pretty straightforward, right? A single core, a pretty straightforward set of other IP and what have you, and that's it. But it's changing, right? So now we're getting more into bigger application processors, companies like Codasip, I know, working on this, and other ones as well. And they're going to have multiple levels of cache on a network on chip, and so on, right? And things like encryption and what have you. So, and this I disagree with you a little bit, because that's the complexity, right, for verification. So whether we like it or not, it's going to get complex. And to verify that, There are ways of doing it, right? But I think moving to a higher level of abstraction, being able to, in that abstraction, actually duplicate the kinds of tests you need for the specific parts of that, and then combining it in some generation technology which actually allows you to bring all this test together and reschedule them is the way to do it, right? And we're still figuring this out, and we're still trying to, I think, as a general industry, work with different people to actually understand how we can actually go about this. But all those components you mentioned are all verifiable, right? And they are all being done today, and I think combining them at a high level and then generating a lot of tests, running them on things like emulation, is the way to go. And just to touch on portable stimulus, what Bodo says is perfectly correct. I know he uses it, so portable stimulus is just a language, right? But the concept behind it and the idea of synthesizing these tests actually addresses a lot of the kinds of things we've been talking about. And I was determined to sit up here and not advertise portable stimulus, even though Brecca uses it as an input format. The real concept, I think, is test synthesis and therefore test generation, however we implement it, right? And if we can synthesize higher level tests, then we can attack some of these kind of complexities that you were talking about, right?
Yeah, one thing that sort of comes into relevance sometimes when you're talking about security is whether you can run your software and then you can inject faults into the system and actually see how your software recovers. Can those faults cause the software to go into places where you didn't expect it to go? And this is one of the other areas where having a virtual platform or a model of your hardware which gives you full flexibility can give you that other extra level of test and verification of things like not memory per se, but the effects of making changes to that memory.
So as far as security, I think what you mentioned, memory encryption and all that, it's a very nice thing to verify. Crypto is always very nice to verify. It's very straightforward. I think the difficult thing really is, especially in processors, is if you extend the processor, are you going to open up a new side channel that can be victim to a side channel attack, right? And that's a really, really hard problem to solve. And we're spending a lot of energy in this, but that's not trivial.
Philippe?
Yeah. Oh, sorry.
I'm not sure how to verify memory, but what I'm sure is each time a new memory appears in the system or we find a new pattern, it needs to be verified inside with the processor, because the pattern of the memory accesses makes slightly change in the processor pipeline, in the processor hazards. And so we have created internally a memory that we call the nasty memory that is doing all the possible nasty patterns. So if we have the performant memory, and if we have the nasty memory, we find very different kind of bug inside the CPU.
Yeah, Ashish, you want to grab a mic?
Yes, so in your experience, what split do you see between functional verification, safety, and security?
So it depends on the application, right?
Yeah.
Obviously, automotive has a huge safety verification component. Security is appearing everywhere now, and then functional is just a solid base that has to be done for every project. I'm not sure. Do you want to give it an application, then we can talk about it?
And I was just thinking, in your experience, like Philippe, Codasip, you guys are making processors. Do you have an idea of how much effort in time and cost, whatever you want to measure, do you split between those three? And anything that you could leverage from the open source domain or from a joint consortium effort, given what Dave alluded to, the cost of the Intels and the ARMs and the AMDs of the world spend internally doing it, what do you reckon is the worldview going forward 2 or 3 years, 4 years from now? What would the RISC-V verification ecosystem look like when it comes to tackling some of the harder problems to get these production-grade processors in cars and other places?
So in Codasip, we are working on the safety very seriously, because the automotive market is a big market, and there is place for RISC-V processor and accelerators here, and Codasip is going into that market. We are the initial stage of implementing the functional safety. It remembers me when Spectrum meltdown bugs appeared 5 years ago, something like that.
2018, yeah.
Sorry?
2018, early 2018.
2018, yes. And every processor, virtually every processor suffers from these bugs. Whatever the vendor, whatever the technology, if there is a predictor, they suffer from these bugs. No one was imagining we can have this kind of side channel attack. So this is really the new thing that we must take into account in the our verification. The first level of verification is making sure it works. The next level is making sure it works even in corner cases. Safety is another problem, and security, making sure the data is not leaking somehow with very smart technology, very smart algorithms. Very difficult task, and it will be the next challenge.
So I gathered that in early days you don't have a lot of recording data of where the split off is.
No,
Which makes sense.
We need prefetchures. Prefetture brings some side channel behaviors from the learning from Spectre and Meltdown. We are aware that this kind of thing exists now, so we are aware. Do we have a robust verification methodology to ensure there is no leak with whatsoever algorithms that have not been yet invented? No, too difficult challenge for the moment.
Yeah, makes sense.
So I think we do have some numbers on this, actually. Firstly, the Siemens guys employ Wilson to do a survey, right? And that has some specific numbers on the number of designs that have safety and security concerns. And I'm trying to remember what the numbers are, but it's quite large. It's like 45%.
I noticed Harry's just walked into the room. See, man.
Oh, okay. So I'm sure you know Harry, right? Those numbers are. I can't remember. Is it?
You're right, your numbers are close, yeah.
Are they like 45%?
50%.
Thank you, on security?
Mm-hmm.
Yeah, so half the designs have security concerns. Some of them are huge and some of them are small, right? And that mirrors about what we see. If I go across our customer base and, you know, where we're asked to look at some security issue, I would say most of our customers have something to look at. And at least a third of them, large components of the test bench is related to security. And it is exactly what you guys are saying. It's like, okay, especially in RISC-V, you want to add an instruction. How is that going to disrupt everything else functionally? How is it going to affect the infrastructure of an SoC in terms of things like coherency, if it's an accelerator, something like that? And then on top of that, what side channel effect have you just introduced and created a vulnerability that some other guy designing some other part of the processor or the SoC has completely not thought about at all? So security is big. I think safety is still more application specific, Harry, right?
Well, the problem is safety is all over the spectrum.
Yeah.
And so if you're only looking at automotive, yeah, it's a lot less, but if you add all the other safety, it's actually pretty high.
Yeah.
It doesn't necessarily represent silicon volume, but what it does represent in terms of a lot of projects are working.
Yeah.
In terms of safety.
And thank you, Harry. Very timely entry into the room. Thank you. And Bodo, go on. Did you want to add anything?
Well, I think, yeah, I mean, I'm not really, I'm still having trouble with the term safety because I work in IBM Z, where 0 stands for zero downtime, so we spend a lot of energy on making this thing secure and resilient against all kinds of soft errors and everything. So we spend a whole lot of effort to do this. I mean, I keep talking, this is one of my hobbies, and I keep talking about this for 20 years, but I haven't seen any company picking up and spending all that energy to verify this in SoCs, for example, because the effort and the price is really high for this. As far as area power is concerned, but also verification energy that needs to be spent. So.
Yeah, go.
Yeah, I was just going to say, we're really we're sort of a tool in the industry, and but as part of that, as part of the RVVI, we accumulate a lot of data, so system variable coverage of the execution of the RTL, the processor core RTL, and also in the reference model space. You get visibility of all the register accesses, all the instructions. So that's sort of not really covering the question, but it is something making things visible into the domain.
Okay, thank you. So let's move across.
So as much as elsewhere from various. By definition, when you talk about processors, you're talking about software. So to what extent do you use software in the verification, not for the sake of software, and how?
So I think Bodo's already touched on that. Do you want to go first, Bodo?
Yeah, so I think there's all kinds of different levels. I mean, in simulation, obviously, our real workloads are seconds of machine time, so we have a hard time to, load all that workload on it. What we do is that we're kind of cutting out key portions of the firmware and integrate them in our test case generators, for example, so we can, include low-level driver codes and things that are very close to interact with the hardware. So that's a lot of stuff that we're doing, and I think that helps us to get functionally correct. But again, that goes back to my previous point. The libraries that we have, just look at AI inference, for example, right? There's a whole lot more than doing matrix multiplication to do AI. How do you prepare the data? How do you get to the data? How fast do you get it back if you want to do real-time inference, right? There's a whole lot more, and we do incorporate that, and we want to do full stack development, but then we really have to go to acceleration and emulation to include that.
And this is something you do, I guess.
Yes.
So, just to clarify the question, let's say between virtual prototyping, simulation, and emulation, and FPGA, or all of that?
All of it.
Yeah. So I would say that, when we're doing test generation, obviously there's a large number of UVM sequences. You get past that, get into the SoC, and most of the test benches have the software component that drives the processor, of course, and then a bunch of transactions that drive the I/O. What we found is sort of similar to what you were saying, Bodo, right? Which is you might start generating software tests for specific functions, but pretty quickly you start to try and bring in firmware that's actually going into production and bring it upstream and actually use some of that to test out the SoC as it's being built up. And we're seeing that more and more and more these days as well. And obviously running on emulation, prototyping, and even actually on the final silicon and reusing those same tests across all that.
Yeah. So Imperius are really coming from the simulation side of things. But what we're trying to introduce is the use of step and compare. So we partner with companies such as Brecker that generate tests, but then by running those tests on the RTL simulation, stepping and comparing that with a reference model, then whenever there's a divergence, you get to stop immediately and see where that divergence is. So when you're running lots of tests, you get to see exactly where things are going wrong very quickly. So you're not having to run millions of cycles of simulation before you go back and analyze your results. You get to stop and examine in real time, essentially.
The software is an external input to the processor. The way software is written, the way it's compiled, the way it's run with the various latency of the memory system brings another source of stimuli to the processor. And in fact, during the development of the processor, having Linux to boot happens quite early in the development of the processor. It's quite easy to have Linux booting to a prompt. Having Linux stable for 1 month with benchmark and load and payloads is a different story. And the next story is also bringing different OSs, bringing FreeRTOS or other OSs, brings different pattern in the way the kernel code is handling the memory management and all the kernel stuff. So having these different OSs to test with payloads, various payloads, brings a lot of quality to the processor verification.
Okay, just before we go back to Asia, there's one right in the corner, Tom. Whilst you're walking over, it's right in the top corner. Whilst you're walking over there, I'll ask one question myself. Bodo, you hinted about this earlier. It's about on performance. I mean, one of the reasons we have RISC-V, we can add instructions that increase performance, and that surely that's going to make our performance verification a lot harder. Certainly not more effort in that direction.
Right, and I think there's two levels of this. I mean, first of all is the focus on performance, because I mean, if designers are drowning in bugs, it's kind of taking a backseat. And when you talk about, right, you start with function, then security, safety, and all of that, performance is not there, right? So it's losing out of focus, and then there's this moment at the end, right, where you say, oh, now I'm putting everything together, and now I see it doesn't perform anymore, right? So I think there's an additional thing that needs to be solved here is that we know. I think we know how to do the function, right? But how do we do a SoC in the beginning to say, okay, so this thing is going to perform and has a market value that we want to build, and how do we maintain that and compare that? I don't think there's anything generic enough right now out there that helps us there, other than doing some very medium to low level performance around it, because I think, and I do believe that software is part of that system.
That's actually part of my question, and I think it was a good start with the software discussion. We talk about getting the hardware right and this kind of things, and that's natural, but I think often we forget about the software part. And not software by running it, but you should have an ecosystem, right? We had a lot of great processors out there, but they failed to have a debugger, to have a good compiler integrated with OS and all the services and things around that. How do we want to address this on the RISC-V side? I think ARM has spent quite a lot of effort to get all these ecosystems integrated in all tools, all compilers in place. How do we want to catch up on this with RISC-V? How do you see that?
So the compiler problem is a big problem when you add an instruction to a processor, because the compiler does not know this instruction, except with CodeASIP. With the language we have developed, the new instruction is known by the synthesis tool delivering the RTL, and we also have half the company working on the compiler, so that the compiler knows and understands this instruction. So in the simple cases where the instruction is data processing, you just recompile your software and the compiler infers these new instructions. Because that's a very big problem. If you can't compile and use a new instruction, it's no use, your processor is no use. So we have the technology to provide that to the customer.
Does this also include debug?
It includes debugs, yes.
Yeah. Sure. And one of the beauties of having an open ISA like RISC-V is that it supposedly encourages not just the hardware guys, but the software guys to create that ecosystem that you're looking for, right? And in fact, Duncan, I mean, you're talking about RVVI, and you guys have done a lot of work on building, a lot of those components and going beyond sort of the standards in terms of some of the tool sets, software tool sets, around RISC-V, and they can use the debug. And I don't want to speak for you, but
Well, yeah. So it's the ecosystem is definitely something that needs to evolve in order to make RISC-V really used widely. But because we were doing reference models, around that reference model we provide the whole debug and tool infrastructure. And tools doesn't mean analysing what the software is doing, so functional tracing, profiling, and all that type of tool, as well as multi-core aware debuggers, and debuggers that are aware of new instructions that are added. Because in the same way as the RTL designers are adding the instructions, then also you add them to the reference models and verify them in the reference models, but then that falls into the tools to allow the debuggers to be aware of those as well.
Okay, is there another question?
Thank you.
Sorry, Ashish, I know you're there, but let me just go to someone else first and answer a question. We'll come back to you. Just one in the middle. You're on my radar, don't worry. Just trying to share the love.
All right. According to your experience, what's the impact on verification effort of the language used for designing your hardware? What I mean is that if you think about the synthesizable subset of system Verilog or HDL is based on very old concepts, so you don't have the object-oriented notions there, you don't have inheritance, anything. If you move to designing your hardware using Chisel or whatever other hardware, the description language that provides more modern concepts like inheritance, etc., would this help verification? Would it make your work easier?
Good question.
yeah.
So I think language is just a tool, and if I speak French, I am more fluent than if I speak English. And I guess the language is just a tool. My answer would be that some people are much more fluent in RTL, in Verilog, some are more fluent in VHDL because they learned this for the last 10 years. So if we take the example of Verilog, system Verilog and VHDL, probably we can put them on the same ballpark of efficiency. If we go to object-oriented or higher level language, we can make the design much faster. If the level of abstraction is correct, no one is writing software code in assembly. Probably that's the fastest implementation, but the slowest and the hardest to debug. Python is getting very popular in terms of software language because it's simpler. It also has some drawbacks, but the adoption has been very wide because of the simplicity. So I guess software is also it's part of tendency and also personal preference. I will not force a Python expert to write C++. I will not force a C++ expert to write Python. That will not work.
Yeah, but you're totally right. So I think we can consider system Verilog, and VHDL in the same ballpark. I was just thinking, if you raise the level of abstraction, you usually have a lower lines of code also.
Yes.
So there are a lot of research that say that your bugs, the bugs that you have in your design, depend somehow on the...
Yeah, but that doesn't necessarily lower my verification effort. I just find less bugs.
Yeah. Okay.
Yeah, I was going to say the same thing. It's true, right? Because, if the description is not complete, right? So you might be, so if you go from the gate level to RTL, you could pretty much describe everything at the gate level in RTL, and yes, you find the bugs. But if you're talking about moving to chisel or moving to some other level of abstraction like that, is all the detail you need in the design contained in that language to actually then find all the bugs that might be contained in that detail? You see what I'm saying? And I would question that.
So actually the thing that Chisel and BlueSpike brings you is verifying multiple configurations with a lot of ease. And the automation that comes with it is orders of magnitude faster than actually what you can do with
Verilog or VHDL. So those high-level languages do provide you certain abstraction mechanisms that do speed up. I mean, Bodo's point, less bugs, but less bugs means less time to debug, overall savings. But whether we solve the validation problem, no. I mean, if you don't know what you were building and you still build the wrong chip, that's not a problem that
So it suggests like a balance between them actually, right?
Yeah.
Which I think is what some people are doing.
The downside, and being on the other side of the spectrum as a verification person, the downside of working with high-level languages is the compilation effort, the translation into Verilog, because at the end of the day, the EDA toolchain only works with Verilog and VHDL. And that's a gap. Can I quickly just ask another question, Well,
let's let the panel finish with that question first. Did you want to add anything on the language question?
I think all I'd say is I see that as similar to, as colleagues have said, in terms of, at higher level languages, you're actually more reliant on the tools. And then translating the bug down here back up to what it was in the code and how that tool created that bug, it becomes harder to fix. So you might have less, but then you have a longer path and harder way it means to get there.
Okay, you've got your time.
Can't wait.
Go ahead, Ashish.
Oh, yeah.
So this is going back to a point that Dave mentioned about using everything we can, simulation, emulation, formal, right? We say that, but we don't really use everything. And I think we all know that based on convenience, a skill set, availability of tools, expertise, we only use things in whatever is available, right? Including portable stimulus and so on. So my question is, given that Intel, having spent years pioneering verification methodologies, had an FDIV moment in mid-90s, when is the RISC-V FDIV moment or something else is going to happen? And what does it take to shift all of the consortiums, open source or non-open source, whether all of the work that Philippe is doing at CodaSip or the other RISC-V vendors, we really do not have a coherent verification methodology that encompasses all of the techniques. All of the stuff that is happening is still scratching the surface. So we aren't actually fully assimilating formal simulation, never mind emulation for a second, to actually pipe clean every processor, right? Let's be honest with us, right? So what will it take to change it, is my question.
So that's a great question. And I think you're right. right? I mean, RISC-V in general is new, and there's a large number of people doing a large number of different kinds of projects all around RISC-V, and therefore employing all kinds of different methodology ideas and what have you, right? Gosh, yeah, if we could predict exactly when we're going to hit that point where there's this universal methodology that everyone exists, you know, we could all go off and buy stock in whatever company the person comes up with that, and we'll all make a lot of money, right? Because right now it's hard to predict. I think the good news is there are a lot of people working on it, and I think based on that, we will see that kind of, you know, more sort of universality, should we say, around the methodology in the next like 2-3 years, something like that. I'm going to predict. Go out on a limb. Don't buy stock.
Anyone else want to take it up?
So hopefully the FDiff bug will come from another company, not Codasip. We are aware of this bug, and all the learning we have from these past bugs, from Spectre and Meltdown, from the experience of verification engineers that have found a lot of bugs, all bring together can give very good methodologies in the end.
Yeah, sorry,
No, sorry, we need to hang on, Ashish. Yeah, go ahead. Yeah, go ahead, Evan.
Yeah, all I was going to say is you know, as we provide and create more standards to help with this, then you know that might bring people together more. So everyone's starting to do more similar things and work together.
Yeah, it's a
hang on.
Sorry,
Brother, did you want to?
Yeah. So I think using all the methods, I mean, and standardization, I'm not sure that all fits well. I think there needs to be something, and that goes back to my previous point, right? You need to pass on testing knowledge to others, architecture knowledge, right? I think that's going to be important, right? Are people gonna pick up and add RISC-V extensions? Do they pick 1, 2, 3, right? They want to pick up the testing knowledge from others, right? And that's the only way how multiple people can learn, right? The question is, you know, where's that knowledge gonna be combined?
Yeah, I just wanted to say, like Philippe's remark on Codasip will not have that. It's a fair remark. I mean, you have confidence in what you're doing. But this doesn't change anything for the rest of the industry, unless competitive knowledge that you're building, or, I mean, we do formal a lot on RISC-V, right? And we often find bugs that simulation miss. But we're a formal verification specialist company. You know, Imperas is a simulations focused company, Breaker is a portable stimulus. You know what I'm saying? That collectively as an industry, I don't think we're doing enough to combine the strengths of all the technologies for RISC-V SoCs. Individually in each company, yes, I think we are going down the same route as the old Intel and IBMs of the world.
Thank you. We have one more question, and then I'm going to wrap up with my question as well. So the last question from the audience, and then we'll do a wrap-up question.
Yeah, it's more of a follow-up on what was just mentioned. This lack of methodology, what I personally see that is really a possible root cause there is that actually the different tools from different vendors are not able to talk to each other when you want to do like formal from one vendor, functional simulation with someone else. Talking about coverage, for instance, it's just not there. I understand why, but I think if we can tackle that, somehow try to talk to our EA guys and make them aware that they're really blocking progress, then we can get to this kind of understanding of, hey, how can we do this methodology?
So we can't run the panel on that as well. In fact, I think I've seen panels on that.
I remember being on a panel 20 years ago.
Yes. So well said. But I think, you know, in fairness to the EDA vendors, and especially the big ones, they are trying, right? There's a lot of work going on in the Accelerator and the standards organizations to bring together, you know, different standards to make all those tools work together. But against that, they've got to differentiate their products, right? And so they're trying to add things and do different things. And sometimes that can trample on some of the standardization work, and people have to make their choice about what they want to do. But I think there is a general sense that there is a need to make all these tools work together, for sure. I mean, Cadence Synopsys people, if they're here, you know, they can comment more than I, right? But I work for both companies, and I remember inside those companies, we talked about this a lot, and how we work with all these people know each other, by the way, in all these companies. They all meet in Accelerator and other organizations, and we all try and do that. So I think you find there is an effort to do it, but it does grate against this need to differentiate, and how do we sort of marry all that up?
Yeah, but
so I actually think there's a huge opportunity here. There's so many people at universities building RISC-V processors. There's tons of people collecting experience now in this, and this is a great thing, right? I can talk to many people now about processor verification. That's just beautiful, right? And I think if we put the community knowledge together and do more open source development for our tools, rather than saying one specific person, I think we can accelerate the learning and be able to make that available. And taking Linux as an example, I can't avoid saying it, but I think for everything, right, whether it's compiler, software, I think that's going to help incredibly, right? And I think that also has to happen for our verification methodologies and the knowledge that I keep talking about.
Okay, Philippe?
Yes, there is a lot of sourcing, a lot of tools already available in the open source world. Let's take the RISC-V example. There is Spike. Spike is a de facto standard as a model. We used it, we tried it, and we are still a customer from Imperas because their model is working a bit faster and there is a nice API to connect, and we are more happy to give them a bit more money and to have something where we can have results faster. Same thing for test generator. There is a Google DV test generator. It does work. We spent a couple of weeks to investigate, to integrate it. It works. And we use some other test generators that find more bugs. Even if we pay more money, we get more results in the end. So that's the differentiation that is also important. Some vendor will have a new technology, and we need to pay for that new technology also, and they want to keep it and to get money from that. So the standard, I think, come only after years when the new technology becomes the standard again. So I think we can be patient and that might come.
Okay, yeah, I always think there's a creative tension between innovation, there's standards and between methodologies and tools, but there's also, you have to be innovative, and that's always to drive our methodologies forward otherwise, but still be doing direct to testing. So there's always the need to drive innovation, and that brings me to the last question, neatly, which is: do we see AI ML being innovation into the way we do our DV?
Well, so we use it, and in a very specific way to do with test generation by sort of. I won't go into all the details, but basically, looking through a graph and figuring out the best path through to generate the best test, for example.
Okay.
And there are other companies, right? So the Verified guys that were acquired by Cadence recently, they had an ML system which handled, looked at groups of regression tests and simplified, which regression tests were the most efficient and which one produced the best results, things like that.
Yeah.
So there's definitely a lot of it being used in different
I've seen the Verified, it's quite impressive. Okay.
Yeah, I think it can help. It can help and assist in a lot of ends, right? Whether it's debugging, whether it's coverage-driven generation where ML can help. Everything around increasing the coverage, but ML can help increase the coverage of if the test bench is capable to create the stimuli. If it can't, you miss the bug.
Yeah.
So it's an helper, not the answer.
Okay. Are you applying it, Philippe?
Yeah, the innovation I have seen in the last 20 years of verification were mostly going to random stimuli that did not exist, that start with Specman and System Verilog kind of recently. And these bring new tests. We had formal recently also that explode a lot, and that's very good, that bring new methodology, new tests. From the experiment I've seen with ML, IA, what I've seen is removing tests that were considered to not bring enough coverage, to not bring more bugs. So I see IA and ML to make the development faster, to have more coverage faster, or to have the same coverage faster, but I don't see it yet to have new tests, new patterns that are created with AI and ML to find the next bugs. So I'm still happy to discuss if someone have a good idea to make that happen, But for the moment, I see this is innovation to reduce the time, but not to bring to the next level of bugs.
Okay. Did you wanna? Okay. And that will be actually our time's up. So that was a neat finish, and I just want to thank Tan for coming, and thank the panel as well for their participation, and thank the audience. We did get questions, which is always good.
And thank you.
And thank you for staying.
Of course, thank you for staying as well. That was the key thing. When we had two in the room, we were it felt painful, but thank you for staying to the end.
Thank you.
We have to stop people.